C6 infinite series, Riemann sum, and definite integral. We already studied the sum of sequence. Here we have a velocity that is measured in a discrete way. That means this delta t is a finite number. However, if you slice this, because this problem is too trivial, we do not have to make use of the integration, but we can compute the area of a triangle. Area triangle is the base times the height, and multiply 1/2. That is very simple. However, using this simple problem, we'd like to develop a mathematical way to reproduce this result and then extend this idea to a more general case. Okay, so I do not have to repeat what we have done with the C2. So previously we sliced this area into small histograms, and we computed the lower sum that is below the curve, and we also computed upper sum that is just above, and we know the area upper sum and lower sum and the genuine area, they satisfy upper sum, lower sum, area, they satisfy this inequality. However, we have found that these two numbers collapses into a single number that is identical to the area, and we use some notation, integral of f of x dx, that represents the area above the x-axis between, this is a curve, we have a lower limit of this integral and upper limit of this integral, area between the curve and x-axis. This is defined by the definite integral. Okay. So to arrive at that single value, what we have done is we have sliced this one into many pieces, and we look for the behavior of the error, whether it diverges or just disappears in the limit as n goes to infinity, and this width approaches 0. Approaches 0 does not mean equals to 0. It is not equal to 0. Instead, it is a very close to 0, arbitrarily small. So that we call infinitesimal. And infinitesimal width and infinite product of infinitesimal width and infinite number of slices, we obtain a finite value of definite integral. So basic idea is this: shrink this delta t as an infinitesimal positive number. So we attach plus, that means it is not equal to 0, but it is arbitrarily close to 0. We say in physics it is a continuum limit. And actually, we have a guitar, and vibrating string of a guitar, it makes sound. However, we can solve this problem. This is an equation of motion for a wave, And that can be achieved by dividing this guitar string into many pieces. So we introduce a model connecting very tiny massive particles that are connected with a massless string. And then we compute the solution for the Newton's law of motion. The final result is approaches the solution first introduced by the Pythagorean people. But in fact, the physical solution is actually different from what Pythagoras has found. By the way, that is not the issue of today. What we want to do is to just have a close look at the integration. Let's see. We know velocity. This is a function. We would like to introduce, we have introduced this sequence, and the value of a velocity at nth step, v0, v1, vn. So we indicate this one to be a continuous function of velocity whose argument is of the discrete value of time. And we know this sequence can be expressed in this manner. Let's see. The position of a particle under constant acceleration called the gravitational acceleration can be expressed in this form, as we have done in C2. In here, Tk is the kth sequence, kth entry of the sequence, identifying the time, discrete time. And that can be expressed in terms of this product. So what we want to measure is the velocity at time t, and what we'd like to do is slice this time t, finite time t, with t over n. So this tiny piece is a small time interval. And where is it? The kth time, that is tk, and that tk is obtained by slicing this one into n pieces and multiply it by k. So if this is k over n is the fraction. K over n is t times k over n, indicates the fraction multiplied by the whole interval. Okay. So velocity is increasing as time goes by, and then we rewrite this one. This delta t is just the gap, this small interval, tiny interval, that is t is divided by n. Okay, so we have found that there is a k dependence. The k dependence can be summed. Okay, this k dependence we know, sigma k, we make use of this formula. But our summation, the upper limit, is n minus 1 instead of n. Therefore, we have this form. In here, there is no k dependence. Therefore, it is constant. This sum is nothing but n minus 1. By the way, we have an overall factor that comes from the tiny interval of a single beam, that is delta t, that can also be expressed as t over n, and we find cancellation of n, and this one becomes 1 over n. In a similar manner, t squared term has such a factor, and n cancels, n minus 1 over a is 1 minus 1 of n. As we take the limit as n goes to infinity, fortunately, these guys they disappear. So the numerical error becomes a 0 as we take the limit as n goes to infinity, keeping the finite width as it is. This is therefore the exact solution, representing the area under the curve, that is the velocity. The t, v, and under this curve, this is the displacement. X of t here, x of t subtracted by x, that is change in position, that is this integral. Okay. We call it, this is a Riemann sum, and this kind of integration can be obtained, we can generalize this one to a more general case. Why don't we replace this velocity? What we have done is a velocity is an integral, that is the displacement. And why don't we generalize this one into more complicated case, that is a power of a unknown x that varies. For simply, we choose from 0 to 1. We know when alpha equals 1, it is just a triangle. When alpha equals to 2, it is a probably curve, and so on. And many of you know very well about this integral whose value is 1 over alpha plus 1. Okay. So can you follow this? What I have done is from a to b, I have sliced this interval, and the difference is b minus a, and I'd like to slice it into n pieces. So this small width is b minus a over n. And we compute the upper sum and lower sum and so on, and take the limit as n goes to infinity. So finally, what we have obtained in the previous class, C2, we just substitute the result for the summation after applying this. So in case we just simply choose a to be 0 and b to be 1, then this integral is simply this, and finally we can obtain this. So integral of x dx 0 to 1, so 1/2, 0 to 1 x squared, 1/3, and so on. So explicit computation is given in here. Here you can see what we have obtained for the general summation formula for complicated one. What we really need is the dominant contribution. That means the highest power of n in this sum. As we increase n arbitrarily large, then the subleading contributions of, for example, you have k, sigma k, from k runs from 1 to n, 1/2 n plus 1. You have 1/2 n squared plus 1/2 n. As n goes to infinity, this guy disappears relative to the dominant contribution. So I can rewrite this one into 1/2 n squared, 1 plus 1 over n. As we increase n arbitrarily large, this subleading contribution disappears. Oh, so we don't have to worry too much about the detailed computation of this explicit formula. That is a headache. Even though we developed a way how to find the most general form of this summation formula. So what I really need when we slice arbitrarily large numbers, then I don't have to worry too much about that. So just power counting is very important. What is the leading piece? So sum of k is n squared something. And then from then on, I don't care about this because, because when I compute this integral in the denominator in here, I have n to the alpha, and this width we have 1 over n. Therefore, we have n to the alpha plus 1. There is a very large number that cancels this. And after that, any subleading piece that appears in the numerator, they will be gone to be 0. I don't have to worry about these kind of detailed calculations. So I'm happy to throw them everything away except for the leading contribution. Okay, so again, we can make use of the mathematical induction to find what happens in the next case, and trivial result will give. I have shifted the power by 1, and this result is identical to that, and except I replaced alpha plus 2, something like that. So what I have done here is that stupid calculation to find out the coefficient of the leading contribution is this. So even though I have listed all the details of the calculation, but at the end of the day, you don't have to worry about that one, but you are left with this result that can be trivially obtained by substituting alpha plus 1 for the previous alpha. That is 1 over alpha plus 1. Okay, in this manner, I can find the integral table for 0 to 1 x to the alpha dx is 1 over alpha plus 1 for any positive integer. And you might do not know much about this integral table, especially the integral table for the half integer. We call the 1/2 or the 3/2, something like that. This was first obtained by another mathematician, Newton. Okay, so to solve physics problem. What you learn in mathematics class is everything, almost 99% was solved by physicists. Don't forget. Anyway, once you develop very simple formula integral table for this kind of integral, and then we'd like to extend to a more general case. What's that? Why don't we replace this one with a different upper limit and lower limit? If you learn calculus, then it is trivial to obtain this. By the way, this kind of way can be obtained by making use of change of variable. A similar method has been already used. For example, let's see. We have x. We studied the case for x runs from 0 to 1. But why don't we replace this one t, that t runs from 0 to 1? And what I like to do is to do the same job, except that x runs from A to B. What should I do? Simple way is rescaling. So we find the origin, shift to the origin. For example, A, B minus A, T and let t vary from 0 to 1. What happens if I substitute 0 for this t, then a plus b minus a0. Aha, that is the lower bound. This is the lower limit. And what happens if I substitute 1, it is a b. Haha, this is a very simple rescaling problem. Okay, so in that case, this integral table can always be generated by the simple integral table that we have obtained, t to the alpha 0 to 1. And the details of calculations are given in here. And let's see. Okay, please follow the details to find out the integral table for changing lower limit and upper limit. Next, do we have to evaluate any integral using the Riemann sum? This is what I have shown to you is to apply Riemann sum method, and this method is not applicable in numerical calculation. In numerical calculation, computer does not know how to deal with infinitesimally small number, and in that case, the final result, as you take the limit n goes to infinity, computer has its own physical limitation. Therefore, the Riemann sum calculation absolutely fails numerically. This one can only be carried out analytically by hand, or let computer forget about the numerical value. Instead, the analytic result using the symbolic manipulation package is possible. By the way, so I do not know how, if I keep doing this job for a very complicated function, it's impossible to finish that calculation until before you die. For example, what I'm doing is from equal to next equal, I have millions of pages. It's analytic result. Mathematician does not calculate that kind of dirty calculation, but physicist does. So in my point of view, this carrying out this calculation, in the end, you will die before you get anything. Therefore, we would like to develop another way that is introduced by Leibniz. It's a clever scientist. You know, this integral notation is developed by Leibniz. Okay, let's see. This is what I previously explained, the change of variable, the realization of change of variable. We can always convert this integral, rescale this integral into a dimensionless integral. As you know, number in physics differs from those in mathematics. Just like that, we can always rescale the problem in a very simple mathematical problem from 0 to 1, isolate the interval, and all of the physical dimension will be factored out of this integral. That is a very efficient way. So this change of variable is one very useful way to simplify the integral or into a form that is already obtained. Another way is also introduced by Leibniz, and in association with the mathematical induction, you can develop very efficient way computing derivative and its inverse operation called integration. Until now, what we have done is this tedious summation. The origin of integration is this tedious summation. However, we shall find that the operation called definite integration is the inverse operation of taking the derivative. Okay, the reason is that there's a function, you slice, and if you increase the upper limit of b by tiny piece, b plus delta, if this with the delta becomes very tiny, what you have obtained additionally is from b to b plus the delta f of x dx. Approximately, this value should be f of b multiplied by delta, something like that. Aha. So the definite integral over a very tiny region from which you can read off the value of the function itself. This is the value of the function at this point if the width is tiny enough. Okay, so, and what is this? This is a tiny number. Aha, what I can do is divide both sides with a tiny number, and f of b can be expressed as this integral from b to b plus delta dx divided by delta. And this one is a tiny number, and this one is a tiny number, because this width is very tiny. Therefore, 0 to 0, the ratio of a very small to very small number. Aha, what's that? This is the derivative. Okay, that means if you integrate and then take the derivative, what you obtain is nothing but the original integrand. We call this one is integrand. So after carrying out integration and then take the derivative, what you have done is nothing but the identity operation. That means you have some action and another action, and that cancels, no change. So we say it is inverse. So integration and differentiation in series means nothing, no change. Okay, that's the reason why I say the definite integral and it's taking the derivative, they are mutually inverse operation. So using that one, because the taking the derivative is a much easier to obtain, so you find various kind of derivative table and just make use of the derivative table to find integral table. And for example, if you do not know how to subtract numbers in elementary school or well before, you just add. Okay? When you count the changes, then you just add before you are acquainted with subtraction, something like that. So don't be afraid of taking the integration. If you're not sure about integration, find out another way. That backdoor is called the differentiation. Okay, who introduced this? Leibniz. Who introduced sigma? Who is he? Find it. He's the person who generalized this idea of Newton applicable to a rigid body, for example, spinning top. That kind of problem, rotation problem, was solved by Euler. And then Euler's idea was passed to the Lagrange, and the Euler-Lagrange equation is the most general form of Newton's law of motion. That's it for today. Thank you.